Right now, as you're watching this video, something extraordinary is happening in laboratories around the world. Scientists are achieving what was once considered impossible, violating every intuition we have about how information and matter should behave in our universe. They're teleporting quantum states across vast distances, instantly transferring information without anything physical traveling through space. And the implications of what they're discovering could fundamentally change everything we thought we knew about the nature of reality itself. Welcome back to another journey into the deepest mysteries of modern physics. I'm absolutely thrilled you've decided to join me tonight as we dive into one of the most mind-bending phenomena in all of science. Tonight, we're not just talking about science fiction fantasies or Hollywood special effects. We're diving into real physics, backed by decades of rigorous experimentation and mathematical proof that has left even the brightest minds in physics struggling to comprehend what they've accomplished. By the time we're finished, you'll understand how scientists have achieved genuine teleportation, why it works in ways that seem to violate common sense, and most importantly, why scaling this phenomenon to human-sized objects represents one of the greatest challenges in modern science. The story begins in the early 1990s when a group of 6 scientists, led by Charles Bennett, made a discovery that would revolutionize our understanding of information transfer. They realized that quantum mechanics, with all its strange and counterintuitive properties, actually provided a pathway to achieve something that classical physics declared impossible. They called it quantum teleportation, and it represents one of the most elegant solutions to a fundamental problem that had puzzled physicists for decades. But here's what makes this discovery truly extraordinary. Quantum teleportation doesn't work the way you might imagine from science fiction movies. There are no shimmering energy fields, no dramatic disappearances and reappearances. Instead, it operates through a process so subtle and precise that it requires understanding some of the deepest principles of quantum mechanics to appreciate its profound implications. To understand how quantum teleportation actually works, we need to start with a phenomenon that Einstein himself called spooky action at a distance. Quantum entanglement represents one of the most counterintuitive aspects of quantum mechanics, where 2 particles become intrinsically linked in such a way that measuring one particle immediately determines the state of its partner, regardless of the distance separating them. This isn't just correlation in the classical sense, where particles might share similar properties due to common origins. This is something far more profound and mysterious. When particles become entangled, their individual quantum states become undefined, existing in a superposition of all possible states simultaneously. But their collective state remains perfectly determined and correlated. It's as if the particles lose their individual identities and become part of a larger quantum system that transcends the normal boundaries of space and distance. The moment you measure one particle and collapse its quantum state into a definite value, its entangled partner instantly assumes the corresponding state, even if it's located on the opposite side of the galaxy. This phenomenon has been demonstrated countless times in laboratories around the world, with experiments showing entangled particles maintaining their mysterious connection across distances measured in hundreds and even thousands of kilometers. The reality of quantum entanglement is no longer in question. What remains mind-boggling is how nature manages to maintain these correlations without any apparent mechanism for communication between the particles. The genius of quantum teleportation lies in how it exploits this entanglement to transfer quantum information without violating the fundamental principles that govern our universe. The process begins with the creation of an entangled pair of particles, with one particle sent to the location where information needs to be transmitted from, traditionally called Alice, and the other particle sent to the destination, traditionally called Bob. Here's where the process becomes truly ingenious. Alice possesses an unknown quantum state that she wants to teleport to Bob. She performs a special type of measurement called a Bell state measurement on both her entangled particle and the unknown quantum state she wishes to transmit. This measurement doesn't reveal the actual information contained in the unknown state, which would be impossible according to the Heisenberg uncertainty principle. Instead, it provides classical information about how the unknown state relates to her entangled particle. The measurement process fundamentally alters both the unknown state and Alice's entangled particle, destroying the original information in the process. This destruction isn't a technological limitation or a flaw in the protocol. It's a fundamental requirement of quantum mechanics that ensures information is never duplicated, adhering to what physicists call the no-cloning theorem. The no-cloning theorem represents one of the most important principles in quantum mechanics, stating that it's impossible to create perfect copies of arbitrary, unknown quantum states. This isn't just a practical limitation based on our current technology, it's a fundamental law of nature that emerges from the mathematical structure of quantum mechanics itself. The theorem ensures that quantum information behaves differently from classical information, which can be copied endlessly without degradation. This no-cloning principle is what makes quantum teleportation both possible and necessary. Because we can't simply copy the unknown quantum state, we need a more sophisticated approach that transfers the state while respecting the fundamental constraints of quantum mechanics. The teleportation protocol achieves this by using entanglement to establish a quantum channel between Alice and Bob, combined with classical communication to provide the additional information needed to complete the transfer. After Alice performs her Bell state measurement, she obtains classical information that she must transmit to Bob through conventional communication channels. This classical information tells Bob exactly what operations he needs to perform on his entangled particle to recreate the original unknown quantum state. When Bob applies these operations, his particle assumes the exact quantum state that Alice originally possessed, completing the teleportation process. The beauty of this protocol is that it achieves perfect state transfer while never violating any fundamental principles of physics. The original state is destroyed during Alice's measurement, ensuring that no cloning occurs. The classical information transmitted from Alice to Bob travels at or below the speed of light, ensuring that no faster-than-light communication takes place. Yet the end result is that quantum information has been transferred from one location to another without any quantum particles actually traveling through the intervening space. Recent breakthrough experiments have demonstrated that this process can work even in noisy, real-world conditions that would seem to make quantum teleportation impossible. Scientists at Northwestern University made headlines when they successfully demonstrated quantum teleportation operating simultaneously with busy internet traffic through the same fiber optic cables. This achievement required identifying specific wavelengths of light that experience minimal interference from classical communication signals, allowing delicate quantum states to survive the journey through networks carrying terabytes of conventional data. The researchers found that by carefully selecting the right frequency channels, quantum photons could navigate through the busy highway of classical internet traffic like skilled drivers weaving through dense traffic without collision. This discovery represents a crucial step toward practical quantum communication networks that can coexist with existing telecommunications infrastructure rather than requiring entirely separate quantum-specific networks. Even more remarkably, other recent experiments have shown that certain types of environmental noise can actually enhance quantum teleportation quality under specific conditions. Researchers in Finland and China discovered that using multipartite hybrid entanglement, which involves entangling different physical properties of particles simultaneously, can create quantum states that become more suitable for teleportation when exposed to particular forms of interference. This counterintuitive finding suggests that the relationship between quantum systems and their environment is far more nuanced than previously understood. These advances have enabled scientists to achieve teleportation fidelities approaching 90% even in the presence of environmental disturbances. Such high-fidelity teleportation opens the door to practical applications in quantum computing and secure communications that were previously considered too fragile for real-world implementation. The distances over which quantum teleportation has been successfully demonstrated continue to grow at an impressive rate. Ground-based experiments have achieved teleportation across hundreds of kilometers using fiber optic networks, but the real breakthrough came with satellite-based demonstrations. Chinese researchers using the Mitzias satellite successfully teleported quantum states between ground stations and the orbiting satellite, covering distances of over 1,400 kilometers and demonstrating that quantum entanglement can survive the harsh conditions of space. These satellite experiments overcome the fundamental limitation of ground-based fiber optic networks, which suffer from exponential signal loss over long distances due to absorption and scattering in optical fibers. By using space-based platforms, researchers can potentially create global quantum communication networks that connect continents through quantum encrypted channels resistant to traditional forms of interception. The implications extend far beyond simple communication. Quantum teleportation enables the creation of distributed quantum computing networks, where quantum processors at different locations can share quantum information instantaneously. This capability could lead to quantum cloud computing services that provide access to quantum computational resources regardless of physical location, similar to current internet-based cloud services, but with quantum advantages that classical systems cannot match. The security implications are equally profound. Quantum teleportation provides the foundation for quantum cryptography systems that are secured by the fundamental laws of physics rather than computational complexity. Any attempt to intercept quantum encrypted communications would necessarily disturb the quantum states involved, immediately alerting legitimate users to the presence of an eavesdropper. This creates communication channels that are theoretically immune to any form of covert surveillance. But as remarkable as these achievements are, they pale in comparison to the ultimate question that captures public imagination. If we can teleport individual particles and even small groups of atoms, what about larger objects? What about complex molecules, living cells, or eventually human beings? This is where the physics becomes both fascinating and deeply challenging. The fundamental obstacle to scaling quantum teleportation to macroscopic objects lies in a phenomenon called decoherence. Quantum states are incredibly fragile, maintaining their coherence only as long as they remain isolated from environmental interference. The larger and more complex an object becomes, the more interactions it has with its surroundings, and the faster its quantum coherence is destroyed. Consider the scale of the challenge. A human being consists of approximately 10 to the 28th power atoms, each potentially in its own quantum state. To teleport a person, we would need to preserve the quantum coherence of this enormous number of particles simultaneously while performing the precise measurements and operations required by the teleportation protocol. The technical challenges are staggering, but the fundamental physics presents even deeper obstacles. The information requirements alone scale exponentially with system size. As quantum systems become more complex, the amount of information needed to describe their complete quantum state grows exponentially rather than linearly. This exponential scaling means that the computational and measurement resources required for teleportation become impossibly large as we move toward macroscopic objects. And if you find yourself drawn to these cosmic puzzles, I'd be grateful if you gave this video a like and perhaps subscribe. Current estimates suggest that even teleporting something as simple as a virus would require quantum error correction and computational capabilities far beyond anything achievable with foreseeable technology. The jump from teleporting individual atoms to teleporting complex biological systems represents not just an engineering challenge, but a fundamental barrier imposed by the laws of quantum mechanics and information theory. Yet recent theoretical work suggests that this barrier might not be absolute. Some researchers have proposed that macroscopic objects might not need to have their complete quantum states preserved for successful teleportation. Since most macroscopic objects exist in what physicists call quasi-classical thermal states, it might be possible to teleport them by focusing only on the classical information that defines their structure and composition, rather than their complete quantum state. This approach would be more akin to an incredibly sophisticated three-dimensional printer that could recreate objects, atom by atom, based on transmitted information about their structure. While this wouldn't be true quantum teleportation in the strict sense, it could achieve the practical goal of reconstructing complex objects at distant locations. The philosophical implications of such technology are profound and troubling. If we could scan and recreate a human being perfectly, atom by atom, would the reconstructed person be the same individual or merely a perfect copy? The original scanning process would necessarily destroy the original person to extract the complete information needed for reconstruction, raising fundamental questions about personal identity and the continuity of consciousness that challenge our deepest assumptions about what it means to be human. These questions become even more complex when we consider that quantum mechanics suggests there might be no objective answer to whether the teleported person is the same individual or a copy. From the perspective of physics, if two systems have identical quantum states, they are indistinguishable in principle. There would be no physical test that could determine which person is the original and which is the copy. As we continue exploring the frontiers of quantum teleportation, we find ourselves confronting not just technical challenges, but fundamental questions about the nature of reality, information, and identity itself. The physics that enables quantum teleportation reveals a universe far stranger and more interconnected than our everyday experience suggests, where information can be transferred without physical travel, and where the act of measurement fundamentally alters the nature of reality. The journey we're embarking on will take us deeper into these mysteries, exploring how scientists are pushing the boundaries of what's possible and what the future might hold for this most impossible of technologies. We'll discover how quantum teleportation connects to the deepest principles of physics and why achieving human-scale teleportation would require us to solve some of the most challenging problems in modern science. The quantum world operates by rules that seem to violate everything our intuition tells us about how reality should work. Yet these same rules might hold the key to technologies that could transform human civilization in ways we're only beginning to imagine. Only beginning to imagine. The story takes an even more intriguing turn when we examine how quantum teleportation relates to other fundamental concepts in physics that seem to offer alternative pathways to instantaneous travel. While quantum teleportation represents a confirmed reality operating in laboratories today, theoretical physics has long explored another possibility that could potentially allow not just information, but actual matter to traverse vast distances instantly. These are the hypothetical structures known as traversable wormholes. Picture space-time not as the flat, unchanging stage that our everyday experience suggests, but as a dynamic fabric that can be bent, twisted, and even folded back on itself. Einstein's general theory of relativity reveals that massive objects warp this space-time fabric, creating the gravitational effects we observe. But the mathematics of general relativity also permits more exotic possibilities, including tunnels through space-time itself that could connect distant regions of the universe. These theoretical wormholes represent shortcuts through the fabric of reality, potentially allowing travel between points separated by vast distances without crossing the intervening space. Imagine folding a piece of paper so that two distant points touch, then poking a hole through both layers. A traveler could move from one point to the other through the hole without traversing the original distance across the paper's surface. Wormholes propose a similar mechanism operating in the four-dimensional fabric of space-time. But here's where the physics becomes truly fascinating and connects directly to our quantum teleportation story. These wormholes, if they could exist in a traversable form, would require something that sounds like pure science fiction, exotic matter with negative energy density. This isn't just matter with negative mass, which would be strange enough, but matter that violates fundamental energy conditions that govern how normal matter behaves in our universe. The energy requirements for creating or maintaining such structures are astronomical, far beyond any conceivable technology. Yet recent theoretical work suggests that the amount of negative energy required might not be as impossibly large as originally calculated. Some physicists propose that quantum effects, particularly the Casimir effect, where virtual particles create measurable forces between closely spaced metal plates, might provide hints about how negative energy could manifest in our universe. What makes this connection to quantum teleportation truly remarkable is a recent breakthrough that demonstrated deep links between wormhole physics and quantum information theory. Researchers using Google's quantum computer successfully simulated the dynamics of information passing through a theoretical, traversable wormhole. Their experiment revealed that the process of information traversing a wormhole is mathematically equivalent to quantum teleportation. This discovery suggests that quantum teleportation and traversable wormholes might be different manifestations of the same underlying physics. The holographic principle that guided these experiments proposes that all the information contained within a volume of space might actually be encoded on its boundary, fundamentally altering our understanding of how information relates to physical space. These experiments don't create actual wormholes, but they demonstrate that the quantum mechanical processes underlying teleportation might be intimately connected to the geometric structure of space-time itself. This connection between quantum mechanics and gravity represents one of the most profound unsolved problems in physics, and quantum teleportation experiments might be providing crucial insights into how these fundamental forces relate to each other. The implications extend beyond academic physics into practical considerations for the future of teleportation technology. If wormholes and quantum teleportation operate through related mechanisms, then advances in quantum information theory might eventually inform approaches to manipulating space-time geometry. Conversely, a deeper understanding of gravitational physics might reveal new approaches to quantum information transfer that transcend current limitations. But let's return to the more immediate challenges facing quantum teleportation as we attempt to scale it toward larger and more complex systems. The exponential scaling problem we discussed earlier represents just one of several fundamental barriers that become increasingly daunting as we move beyond simple atomic systems. Consider the challenge of quantum error correction, which becomes critical when dealing with larger quantum systems. Individual quantum bits, or qubits, are incredibly fragile and prone to errors caused by environmental interference. Current quantum computers require sophisticated error correction protocols that use multiple physical qubits to encode a single logical qubit, providing redundancy that allows errors to be detected and corrected. For quantum teleportation of macroscopic objects, we would need error correction on a scale that staggers the imagination. Each of the billions of quantum states that comprise a complex object would need protection against decoherence, requiring vast arrays of additional quantum systems dedicated solely to error correction. The overhead becomes so enormous that the quantum system needed to teleport a macroscopic object might be larger than the object itself by many orders of magnitude. The timing requirements present another formidable challenge. Quantum teleportation requires precise coordination between measurements at the transmitting location and operations at the receiving location. For a single particle, this coordination is challenging but manageable. For a system containing billions of particles, the timing precision required approaches the limits of what's physically possible. Every quantum operation must be completed within the coherence time of the quantum states involved, which for most systems is measured in microseconds or milliseconds at best. Scaling this to macroscopic systems would require performing impossibly complex operations faster than decoherence can destroy the quantum information we're trying to preserve. Recent research has explored whether these limitations might be circumvented through clever approaches that don't require preserving the complete quantum state of macroscopic objects. Some theorists propose focusing on teleporting only the information necessary to reconstruct classical objects, rather than their full quantum states. This approach recognizes that most macroscopic objects exist in thermal equilibrium states that can be described using classical physics, rather than quantum mechanics. The quantum effects that make individual particles so mysterious tend to average out in large systems, leaving behind classical properties like temperature, pressure, and chemical composition that might be teleportable using more conventional approaches. Imagine a teleportation system that functions more like an incredibly sophisticated scanning and reconstruction device. Such a system would analyze the complete atomic structure of an object, transmit this classical information through conventional communication channels, and then use advanced nanotechnology to rebuild the object atom by atom at the destination. This wouldn't be quantum teleportation in the strict sense, since we're not preserving quantum coherence or using entanglement to transfer quantum states. But it could achieve the practical goal of recreating complex objects at distant locations with perfect fidelity. The original object would still need to be destroyed during the scanning process to extract the complete information needed for reconstruction, maintaining the fundamental principle that prevents copying. The scanning requirements alone present extraordinary challenges. To reconstruct a complex object perfectly, we would need to determine the position and chemical identity of every single atom, along with their bonding relationships and three-dimensional arrangements. This level of detail far exceeds anything achievable with current imaging technology, which struggles to resolve individual atoms even under ideal conditions. For biological objects, the challenges multiply exponentially. Living systems are dynamic, with molecular processes occurring on timescales much faster than any conceivable scanning procedure. The act of scanning would necessarily disrupt the delicate biological processes that define life, raising profound questions about whether the reconstructed object would truly be alive or merely an elaborate molecular sculpture. The energy requirements for such detailed scanning and reconstruction would be enormous. Breaking down complex molecules to extract their structural information requires overcoming the chemical bonds that hold atoms together, while rebuilding those same molecules demands precise energy input to reform those bonds in exactly the right configurations. Current estimates suggest that teleporting even simple biological objects, like bacteria, would require energy levels comparable to small nuclear explosions, focused with precision that exceeds our finest manufacturing capabilities by orders of magnitude. Scaling this to larger organisms multiplies both the energy requirements and the precision demands to levels that seem fundamentally impossible with any conceivable technology. Yet the theoretical possibility remains tantalizing because it doesn't violate any fundamental laws of physics. The information content of any classical object, no matter how complex, is finite in principle. If we could develop sufficiently advanced scanning and reconstruction technologies, along with the massive energy sources and precision control systems required, classical teleportation might eventually become feasible. This possibility has inspired research into what scientists call quantum-enhanced sensing, where quantum mechanical effects are used to achieve measurement precision beyond what's possible with classical instruments. Quantum sensors can detect incredibly weak signals and measure physical properties with accuracy that approaches fundamental limits imposed by quantum mechanics itself. These quantum sensing techniques might eventually enable the detailed scanning capabilities that classical teleportation would require. By using entangled particles as probes, quantum sensors can extract information about complex systems while minimizing the disturbance caused by the measurement process. Recent experiments have demonstrated quantum sensors capable of detecting magnetic fields, gravitational waves, and other phenomena with sensitivity that seemed impossible just decades ago. Some researchers speculate that similar techniques might eventually be applied to scanning the detailed structure of complex objects with the precision needed for faithful reconstruction. The development of advanced nanotechnology provides another piece of the puzzle. If we could build molecular machines capable of assembling complex structures, atom by atom, the reconstruction half of the teleportation process might become feasible. Current research in molecular manufacturing and synthetic biology is making steady progress towards such capabilities, though we remain far from the level of control required for teleporting macroscopic objects. These technological developments raise fascinating questions about the relationship between quantum teleportation and classical reconstruction. Would a perfectly reconstructed object created through classical scanning and rebuilding be equivalent to one created through true quantum teleportation? From a practical standpoint, if both processes create identical end products, the distinction might be purely academic. But from the perspective of fundamental physics, the difference could be profound. Quantum teleportation preserves quantum correlations and entanglements that classical reconstruction might not capture. For most macroscopic objects, these quantum effects might be negligible, but for objects where quantum coherence plays important roles, the distinction could be crucial. Living systems present particularly complex cases because biological processes operate at the interface between quantum and classical physics. While most cellular processes can be understood using classical chemistry and biology, recent research has revealed quantum effects playing important roles in photosynthesis, enzyme catalysis, and possibly even consciousness itself. If quantum effects are indeed crucial for biological function, then classical reconstruction might create objects that appear identical but lack the subtle quantum processes that define life. This possibility adds another layer of complexity to the already formidable challenges of biological teleportation. The philosophical implications become even more intricate when we consider that consciousness itself might depend on quantum effects in the brain. Some theories propose that consciousness emerges from quantum processes in neural microtubules, creating patterns of quantum coherence that define our subjective experience of awareness. If such theories prove correct, then teleporting a conscious being would require preserving not just the classical structure of their brain, but also the delicate quantum states that generate their inner experience. This would make human teleportation dependent on solving some of the deepest mysteries in neuroscience and consciousness studies, fields where our understanding remains primitive despite decades of intensive research. These considerations transform teleportation from a purely technological challenge into a profound exploration of what defines identity, consciousness, and life itself. The physics that makes teleportation possible forces us to confront fundamental questions about the nature of existence that have puzzled philosophers for centuries. As we continue pushing the boundaries of what's possible with quantum teleportation, we find ourselves not just developing new technologies, but exploring the deepest mysteries of reality itself. The quantum world that enables teleportation operates according to principles that challenge everything we thought we knew about information, matter, and the relationship between observation and reality. The quantum realm continues to surprise us with discoveries that push against the boundaries of what we once considered impossible. Recent experiments have revealed that quantum teleportation can operate under conditions that would have seemed utterly hostile to such delicate processes just a few years ago. Scientists have successfully demonstrated teleportation protocols that not only survive in noisy environments, but actually benefit from certain types of interference. This counterintuitive discovery emerged from research into multipartite hybrid entanglement, where researchers entangle different physical properties of particles simultaneously. Instead of relying on a single type of quantum correlation, these systems create multiple entangled connections between particles, providing backup pathways for quantum information transfer when primary channels become corrupted. The results were stunning. When conventional single-property entanglement failed due to environmental noise, the hybrid entangled systems maintained teleportation fidelities approaching 90%. The noise that should have destroyed quantum coherence actually helped stabilize the teleportation process by preferentially affecting certain entangled properties while leaving others intact. This breakthrough fundamentally changes how we think about scaling quantum teleportation to larger systems. If carefully designed quantum states can actually benefit from environmental interference, then the seemingly insurmountable challenge of decoherence might have solutions we haven't yet imagined. The key lies in understanding how different types of quantum correlations respond to various forms of noise and designing teleportation protocols that exploit these interactions rather than fighting against them. The implications extend far beyond laboratory demonstrations. Quantum communication networks operating in real-world conditions face constant challenges from temperature fluctuations, electromagnetic interference, and mechanical vibrations. Traditional approaches focus on isolating quantum systems from these disturbances, requiring expensive shielding and cooling systems that make practical implementation difficult and costly. But if quantum teleportation can be designed to thrive in noisy environments, we might be able to build robust quantum networks that operate alongside existing telecommunications infrastructure without requiring specialized protection. This could dramatically accelerate the deployment of quantum communication technologies by leveraging the massive investments already made in global fiber optic networks. The engineering challenges remain formidable, but recent progress suggests they might be surmountable with sufficient research and development. Teams around the world are working on quantum repeaters, devices that can extend the range of quantum communication by refreshing entangled states at intermediate points along long-distance networks. Current fiber optic networks lose quantum signals exponentially with distance due to absorption and scattering effects that cannot be overcome with classical amplification techniques. Unlike classical signals, quantum states cannot be copied and amplified without destroying their quantum properties. Quantum repeaters solve this problem by creating chains of entangled particles that can transfer quantum states across multiple shorter segments. The process works by establishing entanglement between repeater stations, then using entanglement swapping to connect previously independent entangled pairs. This creates extended quantum channels that can span continents while maintaining the fidelity needed for reliable teleportation. Early demonstrations have shown proof-of-concept systems operating over hundreds of kilometers, with researchers targeting 1,000-kilometer networks within the next decade. These developments bring us closer to practical applications that could transform multiple industries. Quantum teleportation enables quantum key distribution systems that provide theoretically unbreakable encryption for sensitive communications. Financial institutions, government agencies, and healthcare organizations are already investing in quantum cryptography systems that use teleportation protocols to secure their most critical data transfers. The security advantages are compelling because they're based on fundamental physics rather than computational assumptions that might be broken by future technological advances. Any attempt to intercept quantum encrypted communications necessarily disturbs the quantum states involved, immediately alerting legitimate users to potential security breaches. This creates communication channels that remain secure even against adversaries with unlimited computational resources. but the most transformative applications might emerge in quantum computing itself. Distributed quantum computers connected by quantum teleportation networks could share quantum information instantaneously, enabling collaborative computations that exceed what any individual machine could accomplish. This distributed approach could solve the scalability challenges that currently limit quantum computers to relatively small numbers of qubits. Imagine quantum cloud computing services, where users access vast quantum computational resources distributed across multiple facilities worldwide. Complex optimization problems, cryptographic analysis, and scientific simulations could be tackled by quantum networks that combine the processing power of numerous quantum computers without the limitations imposed by classical communication channels. The technical requirements for such networks push against the current state of the art in quantum control systems. Maintaining quantum coherence across multiple connected systems requires unprecedented precision in timing, phase relationships, and error correction protocols. Each quantum operation must be coordinated across the entire network with timing precision measured in nanoseconds or better. Current quantum computers struggle to maintain coherence for more than milliseconds, even in carefully controlled laboratory environments. Scaling this to networks spanning thousands of kilometers introduces additional sources of decoherence and timing uncertainty that compound the existing challenges of quantum error correction. Yet researchers continue making steady progress on each component of the puzzle. Better quantum error correction codes reduce the overhead required to protect quantum information from environmental interference. Improved control systems enable more precise manipulation of quantum states. Advanced materials and fabrication techniques create quantum devices that maintain coherence for longer periods. The convergence of these advances suggests that practical quantum teleportation networks might emerge sooner than many experts expected. Several countries and organizations have announced major investments in quantum communication infrastructure, recognizing the strategic importance of quantum technologies for future economic and security competitiveness. China has deployed the world's first quantum communication satellite and is building ground-based quantum networks connecting major cities. The European Union has launched ambitious quantum flagship programs aimed at developing practical quantum technologies. The United States has established national quantum initiatives with substantial funding for research and development. These investments reflect growing recognition that quantum technologies represent a fundamental shift in information processing capabilities rather than incremental improvements over existing systems. Countries and organizations that successfully develop quantum teleportation networks could gain significant advantages in fields ranging from financial services to scientific research to national security. But scaling quantum teleportation beyond current demonstrations requires solving problems that go far beyond engineering challenges. The fundamental physics of quantum mechanics imposes constraints that become increasingly restrictive as we attempt to teleport larger and more complex systems. The no-cloning theorem that prevents copying of quantum states also limits our ability to create backup copies of quantum information during teleportation processes. If something goes wrong during transmission, there's no way to recover the lost information because the original quantum state was necessarily destroyed during the initial measurement. This creates reliability challenges that don't exist for classical communication systems. Classical information can be copied, stored, and transmitted through multiple redundant channels to ensure reliable delivery. Quantum information must be handled more delicately, with protocols designed to detect and correct errors without ever creating copies of the quantum states being protected. Recent research has explored whether quantum error correction might provide solutions to these reliability challenges. By encoding quantum information across multiple physical qubits, quantum error correction codes can detect and correct certain types of errors without violating the no-cloning theorem. The redundant qubits don't contain copies of the original information, but rather distributed correlations that can be used to reconstruct lost information. These techniques work well for protecting individual qubits or small quantum systems, but they require enormous overhead as system size increases. Each logical qubit might need hundreds or thousands of physical qubits for adequate protection, making the quantum systems required for error correction vastly larger than the information they're designed to protect. For teleporting macroscopic objects, the error correction requirements become astronomical. Every atom in the object might need its quantum state protected by dozens of additional qubits, creating quantum systems with complexity that exceeds anything we could realistically build or control. The computational requirements present equally daunting challenges. Classical computers can simulate quantum systems containing a few dozen qubits, but the computational resources required grow exponentially with system size. Simulating the quantum mechanics of macroscopic objects would require computational capabilities that dwarf the combined processing power of every computer on Earth. This computational barrier affects not just our ability to design teleportation protocols for large objects, but also our capacity to understand and predict their behavior. We're attempting to manipulate systems whose complexity exceeds our ability to model or analyze them theoretically. The measurement challenges compound these difficulties. Quantum teleportation requires precise measurements of quantum states that become increasingly difficult as systems grow larger and more complex. Current techniques can measure individual qubits or small quantum systems with reasonable accuracy, but scaling these measurements to macroscopic objects would require sensor technologies that don't yet exist. Each measurement must be completed within the decoherence time of the quantum system, which typically ranges from microseconds to milliseconds. For large objects containing billions of quantum states, this creates impossible timing constraints, where we would need to perform more measurements than physically possible within the available time window. The energy requirements add another layer of complexity. Quantum teleportation requires creating and maintaining entangled states, which becomes increasingly energy intensive as system size grows. The precise control needed to manipulate large quantum systems would require energy sources and delivery systems with capabilities far beyond current technology. Even the theoretical energy requirements for teleporting macroscopic objects approach those of small nuclear reactors, focused with precision that exceeds our finest manufacturing capabilities by orders of magnitude. The practical engineering challenges of building such systems seem insurmountable with any foreseeable technology. These fundamental barriers suggest that teleporting large objects might require completely different approaches than simply scaling up current quantum teleportation protocols. Some researchers have proposed hybrid techniques that combine quantum teleportation for critical quantum information with classical reconstruction for bulk material properties. Such hybrid approaches might preserve the quantum coherence necessary for complex molecular processes while using more conventional techniques to recreate the classical structure that defines most macroscopic properties. This could potentially reduce the quantum system requirements to manageable levels while still achieving faithful reconstruction of complex objects. The biological implications of such approaches raise profound questions about the nature of life and consciousness. If hybrid teleportation preserves molecular structure but not all quantum correlations, would a teleported organism truly be alive in the same sense as the original? Recent research suggesting quantum effects in biological processes makes this question more than merely philosophical speculation. Photosynthesis, enzyme catalysis, and possibly even consciousness itself might depend on quantum coherence that hybrid teleportation techniques could fail to preserve. The distinction between a perfectly reconstructed biological system and a truly living organism might depend on subtle quantum effects that we don't yet understand well enough to preserve through artificial means. These considerations transform teleportation research from a purely technological endeavour into an exploration of the deepest questions about the nature of existence itself. The quantum mechanics that enables teleportation forces us to confront fundamental mysteries about information, identity, and the relationship between consciousness and physical matter. As we push toward larger and more complex teleportation experiments, we find ourselves not just developing new technologies, but probing the boundaries between the quantum and classical worlds. Each advance reveals new complexities and raises new questions about what it truly means to transfer not just information, but the essence of existence itself across the vast expanses of space and time. The journey ahead promises discoveries that will challenge our understanding of reality in ways we can barely imagine. As we continue exploring the most impossible technology that quantum mechanics has revealed to be not only possible, but inevitable in a universe governed by the strange and wonderful laws of the quantum realm. Quantum realm. The quantum mechanics underlying teleportation protocols reveals a universe operating by principles so fundamentally different from our everyday experience that even seasoned physicists struggle to reconcile what the mathematics predicts with what their intuition suggests should be possible. Yet these same counterintuitive principles might hold the key to understanding why human-scale teleportation represents such an extraordinary challenge. Consider what happens at the most basic level when quantum information is transferred during teleportation. The process doesn't simply move quantum states from one location to another like classical objects being transported. Instead, it involves a complete dissolution of the original quantum information at the source, followed by its perfect reconstruction at the destination using the mysterious correlations preserved in entangled particles. This dissolution isn't accidental or the result of technological limitations. It represents a fundamental feature of how information behaves in the quantum realm. The no-cloning theorem ensures that quantum information cannot exist in multiple copies simultaneously, which means that successful teleportation requires the complete destruction of the original state as an essential part of the process. For individual particles or small quantum systems, this destruction and reconstruction occurs seamlessly, with the teleported state emerging at the destination with perfect fidelity. But as we scale toward larger systems, the complexity of orchestrating this dissolution and reconstruction grows exponentially, creating challenges that push against the fundamental limits of what's physically possible. Recent theoretical work has explored whether the exponential scaling problem might be circumvented through clever encoding schemes that compress the quantum information required to describe complex systems. These approaches recognize that most macroscopic objects don't exist in arbitrary quantum states, but rather in highly structured configurations that might be describable using fewer quantum bits than naive calculations would suggest. The idea draws inspiration from classical data compression, where redundant information in digital files can be eliminated without losing essential content. But quantum information compression faces unique challenges because the no-cloning theorem prevents us from making copies of quantum states to analyze their structure. We must compress quantum information without ever being able to examine what we're compressing. Some researchers have proposed using machine learning techniques to discover patterns in quantum states that might enable more efficient teleportation protocols. These approaches would train artificial intelligence systems on quantum data to identify hidden structures that could reduce the information overhead required for faithful state transfer. The challenge lies in creating training data for such systems without violating quantum mechanical principles. Classical machine learning relies heavily on the ability to copy and manipulate data repeatedly during the training process. But quantum machine learning must operate under the constraint that quantum information cannot be duplicated or stored in classical form without destroying its quantum nature. Early experiments in quantum machine learning have shown promising results for small systems, with algorithms successfully identifying patterns in quantum states that enable more efficient processing and manipulation. These techniques might eventually scale to larger systems, potentially providing pathways around some of the barriers that currently make macroscopic teleportation seem impossible. But even if information compression techniques could reduce the quantum overhead, they cannot eliminate the fundamental timing constraints that become increasingly restrictive as systems grow larger. Quantum coherence time set absolute limits on how long quantum information can be preserved before environmental interference destroys it irreversibly. For typical quantum systems operating at room temperature, coherence times range from microseconds to milliseconds at best. During these brief windows, all the measurements, calculations, and reconstructions required for teleportation must be completed with perfect precision. The complexity of coordinating these operations across macroscopic systems containing billions of quantum states approaches the limits of what's theoretically possible. Recent advances in quantum error correction have extended coherence times somewhat by actively detecting and correcting errors as they occur. These techniques use additional quantum systems to monitor the states being protected, applying corrective operations whenever decoherence is detected. But the overhead required for such protection grows dramatically with system size, potentially requiring more resources for error correction than for the teleportation process itself. The development of topological quantum systems offers another approach to extending coherence times by encoding quantum information in global properties of quantum systems rather than local particle states. These topological qubits are inherently protected against certain types of environmental interference because their quantum information is distributed across the entire system rather than localized in individual particles. Topological protection could potentially enable quantum states to survive much longer in noisy environments, providing the extended coherence times needed for complex teleportation protocols. But creating topological quantum systems requires exotic materials and precisely controlled conditions that remain challenging to achieve even in laboratory settings. The energy requirements for maintaining quantum coherence in large systems present another fundamental barrier. Quantum states naturally tend toward thermal equilibrium with their environment, which typically means losing their quantum coherence and becoming classical. Preventing this thermalization requires constant energy input to maintain the system in its coherent quantum state. For small quantum systems, these energy requirements are modest and can be met using conventional cooling and control techniques. But the energy needed to maintain quantum coherence scales unfavorably with system size, potentially requiring enormous power sources to keep macroscopic quantum systems in coherent states long enough for teleportation. Some researchers have explored whether quantum coherence might be maintained more efficiently by exploiting quantum many-body effects that emerge in large systems. These collective phenomena can sometimes create stable quantum states that resist decoherence more effectively than individual particle states. But understanding and controlling such many-body quantum systems remains one of the most challenging problems in condensed matter physics. The measurement problem presents yet another fundamental obstacle to scaling quantum teleportation. The Bell state measurements required for teleportation must be performed with extraordinary precision on all the quantum states involved simultaneously. Current measurement techniques can handle individual qubits or small quantum systems, but scaling to macroscopic objects would require sensor technologies with capabilities far beyond anything currently imaginable. Each measurement must also be non-destructive for all quantum states except the specific ones being measured for teleportation. This requires measurement techniques that can extract precise information about some quantum states while leaving others completely undisturbed. The technical challenges of achieving such selective measurements become increasingly difficult as system complexity grows. Recent progress in quantum sensing has demonstrated measurement techniques with sensitivity approaching fundamental limits imposed by quantum mechanics. These quantum sensors use entangled probes to achieve measurement precision that classical sensors cannot match, potentially providing the sensitivity needed for the complex measurements required by advanced teleportation protocols. But even quantum-enhanced measurements face fundamental limits imposed by the uncertainty principle and the no-cloning theorem. There are theoretical bounds on how much information can be extracted from quantum systems without destroying the states being measured. These limits become increasingly restrictive as we attempt to measure the complex quantum states required for macroscopic teleportation. The reconstruction phase of teleportation presents equally formidable challenges. After quantum information has been measured and transmitted, it must be used to recreate the original quantum states with perfect fidelity at the destination. This requires quantum manipulation techniques that can construct arbitrary quantum states with precision that exceeds anything currently achievable. Current quantum control systems can manipulate individual qubits or small quantum systems with reasonable accuracy, but the precision required scales exponentially with system complexity. Constructing the quantum states corresponding to macroscopic objects would require control techniques with capabilities that seem fundamentally impossible, given the physical limitations of measurement and manipulation systems. The timing synchronization required between measurement and reconstruction adds another layer of complexity. The classical information obtained from Bell state measurements must be transmitted to the destination and used to guide reconstruction operations, while the quantum states involved retain their coherence. For large systems, this creates timing constraints that approach the speed of light limits for information transfer. Even using the fastest possible communication channels, the time required to transmit the classical information needed for reconstructing complex quantum states might exceed the coherence times of the quantum systems waiting at the destination. This creates a fundamental timing mismatch that could make faithful reconstruction impossible regardless of technological advances. Some researchers have proposed pre-sharing additional entangled states to reduce the classical information that must be transmitted during teleportation. These techniques could potentially reduce communication delays by encoding some reconstruction information in quantum correlations established before the teleportation process begins. But the overhead required for such pre-shared entanglement grows with system complexity, potentially creating resource requirements that exceed what's practically achievable. The philosophical implications of these technical barriers extend far beyond engineering challenges into fundamental questions about the nature of identity and consciousness. Even if all the technical obstacles could somehow be overcome, the fact that teleportation necessarily destroys the original system raises profound questions about whether the reconstructed entity would truly be the same individual or merely a perfect copy. For inanimate objects, this distinction might seem purely academic. If two objects have identical physical properties down to the quantum level, there would be no physical test that could distinguish between the original and the copy. From the perspective of physics, they would be equivalent in every measurable sense. But for conscious beings, the question becomes far more troubling. Would the reconstructed person have the same memories, personality, and subjective experiences as the original? Would they feel continuous with their pre-teleportation existence? Or would they be a new individual who merely believes they have always existed? Recent neuroscience research has revealed that consciousness might depend on quantum effects in neural microtubules and other brain structures. If these quantum processes are essential for generating subjective experience, then teleporting a conscious being would require preserving not just the classical structure of their brain, but also the delicate quantum states that might generate their inner awareness. This requirement would make human teleportation dependent on solving some of the deepest mysteries in consciousness research, fields where our understanding remains primitive, despite decades of intensive investigation. We would need to understand not just how consciousness arises from physical processes, but also which aspects of those processes must be preserved to maintain continuity of personal identity. The ethical implications become even more complex when we consider that the original person would be destroyed during the scanning process required for teleportation. This destruction wouldn't be an unfortunate side effect, but a fundamental requirement of the process. The question becomes whether creating a perfect copy justifies destroying the original, even if the copy would be indistinguishable from the original in every measurable way. These considerations transform teleportation from a purely technological challenge into an exploration of the deepest questions about the nature of existence, identity, and consciousness. The physics that makes teleportation possible forces us to confront fundamental mysteries about what defines a person and whether physical continuity is necessary for personal identity. As research in quantum teleportation continues advancing toward larger and more complex systems, these philosophical questions will become increasingly urgent. The same scientific progress that brings us closer to practical teleportation applications also forces us to grapple with profound questions about the nature of reality and our place within it. The journey toward human-scale teleportation represents more than just a technological quest. It's an exploration of the fundamental limits of what's possible in a universe governed by quantum mechanical principles, and a confrontation with the deepest questions about consciousness, identity, and the nature of existence itself. The answers we discover along the way will reshape not just our understanding of physics, but our understanding of what it means to be human in a quantum universe, where the impossible becomes merely improbable, and the improbable becomes inevitable, given sufficient time and determination to push against the boundaries of what reality allows. The boundaries of what reality allows. The quantum universe operates according to laws so strange and counterintuitive that they challenge everything we thought we knew about the fundamental nature of reality itself. As we stand at the threshold of potentially revolutionary advances in teleportation technology, we find ourselves confronting not just technical hurdles, but barriers that seem to emerge from the very fabric of existence. Recent experimental breakthroughs have revealed phenomena that would have seemed like pure fantasy just decades ago. Scientists working with increasingly sophisticated quantum systems have discovered that the boundaries between the quantum and classical worlds are far more fluid than anyone previously imagined. These discoveries are reshaping our understanding of what might eventually become possible as we push toward larger and more ambitious teleportation experiments. Consider the remarkable progress being made in quantum sensing technologies that could eventually enable the precise measurements required for complex teleportation protocols. Researchers have developed quantum sensors capable of detecting magnetic fields with sensitivity that approaches the theoretical limits imposed by quantum mechanics itself. These devices can measure changes so subtle that they're measured in units smaller than the diameter of atomic nuclei, yet operating in laboratory conditions that would have seemed impossibly noisy just years ago. The implications for teleportation research are profound. If we can measure quantum states with such extraordinary precision, we might eventually develop the sensing capabilities needed to scan and analyze complex quantum systems without destroying the information we're trying to preserve. This represents a crucial step toward overcoming one of the fundamental barriers that currently makes macroscopic teleportation seem impossible. But even these advances in quantum sensing face fundamental limitations that become increasingly restrictive as we attempt to scale toward larger systems. The uncertainty principle doesn't just limit our ability to measure individual particles, it imposes constraints on how much information can be extracted from any quantum system without fundamentally altering its state. These constraints don't disappear As our measurement technology improves, they represent absolute limits imposed by the mathematical structure of quantum mechanics itself. The challenge becomes even more daunting when we consider the distributed nature of quantum information in complex systems. Unlike classical information, which can be localized in specific components of a system, quantum information in entangled systems exists in the correlations between particles rather than in the particles themselves. Measuring these correlations requires techniques that can probe the relationships between widely separated components simultaneously, creating measurement challenges that scale exponentially with system complexity. Recent theoretical work has explored whether these measurement challenges might be addressed through novel approaches that exploit the collective properties of quantum many-body systems. Some researchers propose that large quantum systems might exhibit emergent behaviors that make them easier to measure and manipulate than the sum of their individual components would suggest. These emergent quantum phenomena arise when large numbers of quantum particles interact in ways that create collective behaviors not present in smaller systems. Just as flocks of birds exhibit coordinated movement patterns that emerge from simple rules followed by individual birds, quantum many-body systems can display collective quantum states that might be more robust and easier to control than isolated particle states. The mathematics describing these emergent quantum phenomena are extraordinarily complex, requiring computational techniques that push against the limits of what's possible with classical computers. Ironically, understanding these systems well enough to exploit them for teleportation might require quantum computers more sophisticated than anything we currently possess. This creates a fascinating recursive challenge where advancing teleportation technology depends on quantum computational capabilities that might themselves require teleportation-like techniques for optimal performance. Quantum computers operating across distributed networks connected by quantum teleportation channels could potentially tackle computational problems that no individual machine could solve, including the theoretical challenges of understanding quantum many-body systems. The energy landscape surrounding these challenges presents another layer of complexity that researchers are only beginning to understand. Quantum states naturally evolve toward thermal equilibrium with their environment, which typically means losing their quantum coherence and becoming classical. Maintaining quantum coherence in large systems requires constant energy input to counteract this natural tendency toward thermalization. But recent discoveries have revealed that the relationship between energy and quantum coherence is far more nuanced than simple thermodynamic arguments would suggest. Under certain conditions, adding energy to quantum systems can actually enhance their coherence rather than destroying it. This counterintuitive behavior emerges from the complex interplay between quantum correlations and environmental interactions in ways that classical physics cannot predict or explain. These discoveries suggest that the energy requirements for maintaining quantum coherence in large systems might not scale as unfavorably as pessimistic estimates have suggested. By carefully designing the energy landscape surrounding quantum systems, researchers might be able to create conditions where quantum coherence becomes more stable rather than more fragile as system size increases. The practical implications extend far beyond teleportation into quantum computing, quantum sensing, and quantum communication technologies that could transform multiple aspects of modern civilization. Quantum computers that maintain coherence across large numbers of qubits could solve optimization problems that currently require centuries of classical computation time. Quantum sensors operating with enhanced coherence could detect gravitational waves, dark matter interactions, and other fundamental phenomena with unprecedented sensitivity. But perhaps the most intriguing possibility is that enhanced quantum coherence might reveal entirely new physics operating at the boundary between quantum and classical behavior. Most of our understanding of quantum mechanics comes from studying small systems where quantum effects dominate, or large systems where classical behavior emerges from quantum foundations. The intermediate regime, where quantum and classical effects compete on equal terms, remains largely unexplored territory. This intermediate regime might be precisely where the most interesting phenomena relevant to macroscopic teleportation occur. If quantum coherence can be maintained across larger systems than previously thought possible, we might discover collective quantum behaviors that enable teleportation protocols fundamentally different from those designed for individual particles. The information theoretic aspects of these challenges reveal deep connections between quantum mechanics and fundamental questions about the nature of information itself. Classical information theory treats information as an abstract quantity that can be copied, stored, and manipulated without regard to the physical systems that encode it. But quantum information theory reveals that information and physics are intimately connected in ways that classical theories cannot capture. The no-cloning theorem represents just one example of how quantum information behaves differently from classical information. But there are many other quantum information phenomena that have no classical analogues and might be crucial for understanding how to scale teleportation to larger systems. Quantum error correction, quantum cryptography, and quantum computational complexity all involve information processing concepts that emerge uniquely from quantum mechanics. Understanding these quantum information phenomena becomes increasingly important as we attempt to design teleportation protocols for complex systems. The classical information required to describe macroscopic objects scales linearly with the number of particles involved, but the quantum information required to describe their quantum state scales exponentially. This exponential scaling creates information processing challenges that dwarf anything encountered in classical physics or computer science. Recent advances in quantum error correction have revealed techniques for protecting quantum information that might eventually scale to larger systems. These techniques don't simply protect individual quantum states, but rather create distributed encoding schemes where quantum information is spread across multiple physical systems in ways that provide natural protection against certain types of errors. The most sophisticated quantum error correction codes create logical qubits that are encoded across hundreds or thousands of physical qubits, providing protection against errors that would destroy individual particle states. These codes can correct not just random errors caused by environmental interference, but also systematic errors that might arise from imperfect control systems or measurement techniques. But implementing quantum error correction for macroscopic teleportation would require encoding schemes of unprecedented complexity and scale. Every atom in a macroscopic object might need its quantum state protected by additional quantum systems, creating error correction overhead that could dwarf the original object by orders of magnitude. The computational requirements for managing such complex error correction schemes approach the limits of what might be physically possible. Classical computers cannot efficiently simulate the behavior of large quantum systems, which means that designing and controlling quantum error correction for macroscopic objects would require quantum computational capabilities that we're only beginning to develop. This creates another recursive challenge, where advancing teleportation technology requires quantum computational capabilities that might themselves depend on teleportation-like techniques for optimal performance. The solution might require developing hybrid classical quantum computational systems that can tackle different aspects of the teleportation problem using the most appropriate computational approaches. The materials science challenges underlying these quantum technologies are equally formidable and represent active areas of research that could determine the ultimate feasibility of large-scale quantum systems. Creating quantum devices that can maintain coherence for extended periods requires materials with properties that barely exist in nature and must be engineered using techniques that push against the limits of current manufacturing capabilities. The most promising approaches involve creating artificial materials with quantum properties tailored for specific applications. These quantum metamaterials can exhibit behaviors that don't occur in naturally occurring substances, including enhanced quantum coherence, controllable entanglement properties, and resistance to environmental decoherence. Recent breakthroughs in materials science have demonstrated quantum metamaterials that can maintain quantum coherence at higher temperatures and for longer periods than naturally occurring quantum systems. These advances bring practical quantum technologies closer to reality by reducing the extreme cooling and isolation requirements that currently limit quantum devices to specialized laboratory environments. But scaling these materials, science advances to the quantities and complexities required for macroscopic teleportation remains a daunting challenge. Creating enough quantum metamaterial to encode and manipulate the quantum states of macroscopic objects would require manufacturing capabilities that exceed current industrial capacity by orders of magnitude. The precision requirements for such manufacturing are particularly challenging because quantum properties are extraordinarily sensitive to tiny variations in material structure and composition. Imperfections that would be negligible for classical materials can completely destroy quantum coherence, requiring manufacturing tolerances that approach atomic scale precision across macroscopic dimensions. As we continue pushing toward these seemingly impossible goals, we find ourselves exploring not just the limits of current technology, but the fundamental boundaries of what might be achievable within the laws of physics as we currently understand them. The quantum mechanics that enables teleportation operates according to principles so counterintuitive that even understanding them requires abandoning many of our most basic assumptions about how reality works. Yet these same counterintuitive principles might hold the key to achieving teleportation capabilities that seem impossible from our current perspective. The history of quantum mechanics is filled with discoveries that initially seemed to violate common sense, but eventually led to technologies that transformed human civilization. Quantum tunneling enabled the electronics revolution. Quantum entanglement is enabling quantum communication networks. And quantum superposition is the foundation of emerging quantum computational technologies. The path toward human-scale teleportation might follow a similar trajectory, with seemingly insurmountable barriers eventually yielding to insights that reveal entirely new approaches to manipulating quantum information. The exponential scaling problems that currently make macroscopic teleportation seem impossible might be circumvented by discoveries that exploit quantum phenomena we haven't yet learned to control or even fully understand. The timeline for such breakthroughs remains impossible to predict because they depend on fundamental advances in our understanding of quantum mechanics that could emerge tomorrow or might require decades of additional research. What seems certain is that the quest to achieve human-scale teleportation is driving advances in quantum science and technology that will transform our understanding of reality, regardless of whether the ultimate goal proves achievable. The journey itself is revealing aspects of the quantum world that challenge everything we thought we knew about information, matter, and the relationship between observation and reality. Each experiment pushes against barriers that seemed absolute. Each theoretical breakthrough opens possibilities that seemed forbidden, and each technological advance brings us closer to capabilities that would have seemed like pure magic to previous generations of scientists. As we stand at this extraordinary moment in the history of science, surrounded by quantum phenomena that defy intuition and approaching technological capabilities that challenge our understanding of what's possible, we find ourselves not just developing new technologies, but exploring the deepest mysteries of existence itself. The quantum universe continues revealing secrets that reshape our understanding of reality in ways we're only beginning to comprehend. The quest to understand these quantum barriers has led scientists to conduct experiments that push the very boundaries of what measurement and control systems can achieve. In laboratories around the world, researchers are developing techniques that could eventually bridge the gap between teleporting individual particles and manipulating the quantum states of increasingly complex systems. One of the most promising developments involves the creation of quantum networks, where multiple quantum processors share entangled states across vast distances. These distributed quantum systems don't just enable faster communication, they create entirely new computational architectures where quantum information can be processed collectively across multiple locations simultaneously. Imagine quantum computers in Tokyo, London, and New York working together on a single computation, sharing quantum states instantaneously through teleportation channels. The computational power of such networks could exceed what any individual quantum computer could achieve, potentially providing the processing capabilities needed to tackle the exponential complexity of macroscopic teleportation. But even these distributed quantum networks face fundamental limitations imposed by the structure of quantum mechanics itself. The entanglement that enables quantum teleportation is fragile and finite. Creating enough entangled connections to support large-scale quantum networks requires resources that scale exponentially with the size and complexity of the systems involved. Recent theoretical work has explored whether these resource requirements might be reduced through quantum network topologies that optimize entanglement distribution. Instead of requiring direct entangled connections between every pair of quantum processors, these optimized networks use intermediate nodes to route quantum information efficiently while minimizing the total entanglement overhead. The mathematics underlying these optimization problems are extraordinarily complex, involving graph theory, quantum information theory, and computational complexity in ways that push against the limits of current theoretical understanding. Solving these problems requires insights that bridge multiple fields of mathematics and physics, creating interdisciplinary challenges that no single researcher or even research group can tackle alone. The collaborative nature of these challenges mirrors the distributed quantum systems they're designed to optimize. Just as quantum networks share computational resources across multiple processors, the theoretical understanding needed to design such networks requires intellectual resources shared across multiple research communities worldwide. This collaborative approach has already yielded surprising insights into the fundamental nature of quantum information and how it relates to space-time geometry. The holographic principle that connects quantum teleportation to wormhole physics suggests that quantum information and gravitational phenomena might be different aspects of the same underlying physical reality. These connections between quantum mechanics and gravity represent some of the deepest unsolved problems in theoretical physics. Understanding how quantum information relates to space-time structure could revolutionize our understanding of both quantum mechanics and general relativity, potentially revealing new approaches to manipulating quantum states that transcend current limitations. The experimental verification of these theoretical connections requires precision measurements that challenge the capabilities of current scientific instruments. Detecting the subtle quantum effects that link information transfer to gravitational phenomena demands sensitivity levels that approach the theoretical limits imposed by quantum mechanics itself. Recent advances in quantum sensing have demonstrated measurement techniques that achieve these extraordinary sensitivity levels for small systems under carefully controlled conditions. Quantum gravimeters can detect changes in gravitational fields that are smaller than the effects produced by moving a paperclip 1 meter away. Quantum magnetometers can measure magnetic field variations caused by the magnetic moments of individual atomic nuclei. These quantum sensing capabilities are approaching the precision needed to probe the connections between quantum information and space-time geometry directly. Future experiments might be able to measure how quantum teleportation processes affect the local curvature of spacetime, providing empirical tests of theoretical predictions that currently exist only in mathematical form. But scaling these quantum sensing techniques to study macroscopic systems presents challenges that mirror those facing teleportation research itself. The quantum states that enable extraordinary measurement precision are just as fragile as those required for teleportation, becoming increasingly difficult to maintain as system complexity grows. The noise sources that limit quantum sensing performance are often the same environmental factors that cause decoherence in teleportation experiments. Temperature fluctuations, electromagnetic interference, and mechanical vibrations all contribute to measurement uncertainty in ways that scale unfavorably with the size and complexity of the systems being studied. Recent research has explored whether the noise-enhanced teleportation techniques discovered for small systems might also improve quantum sensing performance for larger systems. If environmental interference can be engineered to enhance rather than degrade quantum performance, it might be possible to create quantum sensors that become more rather than less precise as they scale to larger sizes. These possibilities remain largely theoretical because the conditions required for noise-enhanced quantum performance are extremely specific and difficult to maintain across large systems. The types of noise that enhance performance for one quantum process might degrade performance for others, creating optimization challenges that require simultaneous consideration of multiple competing effects. The energy landscapes underlying these optimization problems reveal deep connections between quantum mechanics and thermodynamics that researchers are only beginning to understand. Quantum systems exist in energy landscapes that can be far more complex than anything encountered in classical physics, with multiple energy minima separated by barriers that can be traversed through quantum tunneling effects. These complex energy landscapes create opportunities for quantum systems to access states and behaviors that would be forbidden in classical systems. But they also create challenges for controlling quantum evolution because small changes in system parameters can lead to dramatically different outcomes through quantum tunneling and interference effects. Understanding and controlling these quantum energy landscapes becomes increasingly important as we attempt to design teleportation protocols for complex systems. The quantum states involved in macroscopic teleportation would exist in energy landscapes of extraordinary complexity with billions of potential pathways that quantum evolution could follow during the teleportation process. Recent advances in quantum control theory have developed techniques for navigating these complex energy landscapes using carefully designed control pulses that guide quantum evolution along desired pathways. These quantum control techniques can achieve remarkable precision for small systems, enabling quantum operations that would be impossible using simple control approaches. But scaling quantum control to macroscopic systems requires understanding energy landscapes whose complexity exceeds current theoretical and computational capabilities. The number of potential quantum pathways grows exponentially with system size, creating navigation problems that dwarf anything encountered in classical control theory. The computational challenges of designing optimal control sequences for large quantum systems have led to the development of machine learning approaches that can discover effective control strategies through automated optimization rather than analytical design. These quantum machine learning techniques use artificial intelligence to explore the vast space of possible control sequences and identify strategies that achieve desired quantum operations. Early results from quantum machine learning research have been remarkably successful for small systems, with algorithms discovering control sequences that outperform strategies designed by human experts. These machine learning approaches might eventually scale to larger systems, providing automated methods for designing the complex control sequences needed for macroscopic teleportation. But quantum machine learning faces unique challenges that don't exist in classical machine learning applications. The no-cloning theorem prevents quantum machine learning algorithms from making copies of quantum data for repeated analysis, forcing them to learn from quantum information that can only be measured once before being destroyed. This constraint fundamentally changes how machine learning algorithms must operate in quantum contexts. Classical machine learning relies heavily on the ability to analyze training data repeatedly from different perspectives, building understanding through multiple passes over the same information. Quantum machine learning must extract understanding from quantum information that can only be examined once. Recent theoretical work has explored quantum machine learning algorithms that can operate under these constraints while still achieving effective learning performance. These algorithms use quantum superposition and entanglement to process quantum information in parallel, potentially extracting more information from single measurements than classical algorithms could obtain from repeated analysis. The development of these quantum machine learning techniques represents another example of the recursive challenges that emerge throughout quantum teleportation research. Advancing teleportation capabilities requires machine learning tools that themselves depend on quantum information processing techniques closely related to teleportation. The philosophical implications of these recursive relationships extend far beyond technical considerations into fundamental questions about the nature of knowledge and understanding in quantum systems. If quantum machine learning algorithms can discover control strategies for quantum systems that human researchers cannot understand or analyze, what does this mean for our ability to predict and control quantum phenomena? This question becomes particularly acute when we consider that quantum machine learning algorithms might eventually discover approaches to macroscopic teleportation that transcend current theoretical understanding. These algorithms could potentially identify quantum control strategies that work in practice while remaining incomprehensible to human researchers using current theoretical frameworks. The possibility that quantum systems might be controllable through methods that exceed human theoretical understanding represents a profound shift in how we think about scientific knowledge and technological development. Throughout human history, technological advances have generally followed from theoretical understanding, with practical applications emerging after scientists developed mathematical frameworks for predicting and explaining physical phenomena. But quantum machine learning suggests that this relationship between theory and practice might be reversed in quantum systems. Practical quantum technologies might emerge from automated discovery processes that identify effective strategies without providing human comprehensible explanations for why those strategies work. This reversal could accelerate the development of quantum technologies, including teleportation systems, but it would also create new challenges for ensuring the safety and reliability of systems whose operation transcends human understanding. How do we validate the safety of teleportation protocols discovered by machine learning algorithms that operate through mechanisms we cannot analyze or predict? The safety considerations become particularly important when we consider the irreversible nature of teleportation processes. The no-cloning theorem ensures that teleportation necessarily destroys the original quantum states being transferred. If something goes wrong during a teleportation process, there's no way to recover the lost information because no backup copies exist. For inanimate objects, this irreversibility might be acceptable if the benefits of teleportation outweigh the risks of information loss. But for living systems, the stakes become far more serious because the information being destroyed and reconstructed includes whatever quantum processes might be essential for life and consciousness. Recent advances in understanding biological quantum phenomena have revealed that quantum effects play important roles in photosynthesis, enzyme catalysis, and possibly even consciousness itself. If these quantum processes are essential for biological function, then teleporting living systems would require preserving quantum coherence across the complex molecular networks that define life. This requirement would make biological teleportation dependent on solving some of the deepest mysteries in biophysics and consciousness research. We would need to understand not just how quantum effects contribute to biological processes, but also which aspects of these processes must be preserved to maintain the continuity of life and consciousness. The experimental challenges of studying quantum effects in biological systems are formidable because living systems operate at temperatures and in environments that typically destroy quantum coherence within microseconds or milliseconds. Yet somehow, biological systems manage to exploit quantum effects for crucial processes like energy transfer and enzymatic catalysis. Understanding how biological systems maintain and exploit quantum coherence under conditions that would destroy it in artificial quantum systems could provide crucial insights for developing more robust quantum technologies, including teleportation systems. If we can understand how life preserves quantum information in noisy biological environments, we might discover techniques for preserving quantum coherence in the artificial systems needed for macroscopic teleportation. Recent research has suggested that biological systems might use quantum error correction mechanisms that are fundamentally different from those developed for artificial quantum systems. Instead of using additional quantum systems to detect and correct errors, biological quantum error correction might exploit the natural redundancy and robustness built into evolutionary optimized molecular networks. These biological approaches to quantum information processing represent a completely different paradigm from the highly controlled artificial quantum systems used in current teleportation experiments. Biological quantum systems operate in warm, noisy environments, using molecular components that would seem impossibly crude compared to the precisely engineered quantum devices used in physics laboratories. Yet biological quantum systems achieve remarkable performance levels that artificial systems struggle to match even under ideal laboratory conditions. Photosynthetic quantum energy transfer operates with efficiency levels that exceed 90% under natural sunlight conditions that would completely destroy the coherence of artificial quantum systems. Understanding the principles underlying this biological quantum robustness could revolutionize our approach to designing quantum technologies, including teleportation systems. Instead of fighting against environmental interference through isolation and error correction, we might learn to work with environmental interactions in ways that enhance rather than degrade quantum performance. The biomimetic approach to quantum technology development represents one of the most promising directions for overcoming the scalability challenges that currently limit teleportation to microscopic systems. If we can understand how biological systems scale quantum information processing from molecular to cellular to organism levels, we might discover principles for scaling artificial quantum systems in similar ways. But the complexity of biological quantum systems presents extraordinary challenges for understanding their operation well enough to mimic their performance artificially. Living systems integrate quantum and classical information processing across multiple organizational levels simultaneously, creating hierarchical information processing architectures of staggering complexity. Current theoretical frameworks struggle to describe even the simplest biological quantum phenomena because they operate at the intersection of quantum mechanics, biochemistry, thermodynamics, and information theory in ways that exceed the scope of any single theoretical approach. Understanding biological quantum systems requires interdisciplinary collaboration across fields that have traditionally operated independently. The collaborative research networks emerging to tackle these challenges mirror the distributed quantum systems they're designed to understand. Just as biological systems integrate information processing across multiple organizational levels, understanding biological quantum phenomena requires integrating knowledge across multiple research disciplines and experimental approaches. These collaborative networks are beginning to reveal the extraordinary sophistication of biological quantum information processing and how it might inform the development of artificial quantum technologies. The insights emerging from this research suggest that the path toward macroscopic teleportation might require fundamental changes in how we approach quantum system design and control. Instead of trying to isolate quantum systems from their environments, we might need to learn how to engineer environmental interactions that support rather than degrade quantum information processing. Instead of using brute force error correction to protect quantum information, we might need to discover how to design quantum systems that are inherently robust against the types of errors they're most likely to encounter. These paradigm shifts could eventually lead to quantum technologies, including teleportation systems that operate more like biological systems than current artificial quantum devices. Such bio-inspired quantum systems might be capable of maintaining quantum coherence across much larger scales and for much longer periods than anything achievable using current approaches. The timeline for developing such revolutionary quantum technologies remains impossible to predict because it depends on advances in our understanding of biological quantum phenomena that are only beginning to emerge. What seems certain is that the quest to achieve macroscopic teleportation continues driving advances in quantum science that are revealing fundamental connections between physics, biology, and information theory. These connections are reshaping our understanding of life itself and how consciousness emerges from quantum processes operating across the complex molecular networks that define biological systems. The same quantum phenomena that enable teleportation might also be essential for the existence of conscious experience itself. As we continue pushing toward the seemingly impossible goal of human-scale teleportation, we find ourselves exploring not just the limits of quantum technology, but the deepest mysteries of what it means to be alive and conscious in a quantum universe, where information and matter, mind and reality exist in relationships far more intimate and mysterious than we ever imagined possible. The convergence of all these quantum phenomena points toward a future where the boundaries between science fiction and scientific reality continue to blur in ways that challenge our fundamental assumptions about what's possible. As we stand at this extraordinary crossroads in human knowledge, laboratories around the world are conducting experiments that push quantum teleportation closer to practical applications that could transform civilization itself. Consider the quantum communication networks already being deployed across multiple continents. China's quantum communication satellite has successfully demonstrated teleportation protocols operating across distances that span from Earth's surface to low orbital platforms over 1,400 kilometers away. European research consortiums are building ground-based quantum networks, connecting major cities through fiber optic infrastructure that carries both classical internet traffic and delicate quantum states simultaneously. These developments represent more than technological achievements. They're creating the foundational infrastructure for what researchers call the quantum internet, a global network where quantum information can be shared instantaneously between connected nodes, regardless of physical distance. The implications extend far beyond faster communication into realms that could redefine how we understand privacy, security, and the nature of information itself. Quantum cryptography systems based on teleportation protocols provide security guarantees that are fundamentally different from anything classical encryption can offer. Instead of relying on mathematical complexity that future computers might eventually overcome, quantum encryption is protected by the laws of physics themselves. Any attempt to intercept quantum encrypted communications necessarily disturbs the quantum states involved, immediately alerting legitimate users to potential security breaches. Financial institutions are already investing billions in quantum cryptography infrastructure, recognizing that quantum computers powerful enough to break current encryption methods might emerge within decades. Government agencies responsible for protecting national security information are implementing quantum communication systems that could remain secure even against adversaries with unlimited computational resources. But the most transformative applications might emerge from distributed quantum computing networks, where quantum processors at different locations share quantum information through teleportation channels. These quantum cloud computing systems could tackle optimization problems, drug discovery challenges, and scientific simulations that would require centuries of computation time using classical approaches. The collaborative potential becomes even more remarkable when we consider how quantum teleportation enables forms of information sharing impossible with classical systems. Quantum computers connected through teleportation networks don't just communicate faster than classical systems. They can share quantum states that exist in superposition across multiple locations simultaneously, creating distributed quantum systems with computational capabilities that transcend what any individual machine could achieve. Recent experiments have demonstrated proof-of-concept quantum networks where entangled quantum processors perform coordinated calculations on shared quantum data. These distributed quantum computations achieve results that neither processor could produce independently, suggesting that quantum networking might enable entirely new categories of problem-solving approaches. The scaling challenges that limit individual quantum computers might be circumvented through networking approaches that distribute quantum computations across multiple smaller systems. Instead of building single quantum computers with thousands of qubits, which requires maintaining quantum coherence across enormous systems, quantum networks could achieve similar computational power by connecting hundreds of smaller quantum processors through teleportation channels. This distributed approach could potentially overcome many of the technical barriers that currently limit quantum systems to laboratory demonstrations. Individual quantum processors with dozens of qubits are becoming increasingly reliable and could be manufactured using existing semiconductor fabrication techniques. Connecting these smaller systems through quantum networks might provide a more practical pathway toward large-scale quantum computing than attempting to build monolithic quantum systems with thousands of qubits. The error correction advantages of distributed quantum systems are particularly compelling. Instead of requiring perfect quantum error correction within individual processors, distributed systems can use teleportation protocols that are inherently protected against certain types of errors. The no-cloning theorem that prevents copying of quantum information also prevents certain classes of errors from propagating through quantum networks in ways that would be catastrophic for classical systems. Recent theoretical work has revealed that quantum networks with carefully designed topologies can actually become more robust against errors as they grow larger, contrary to the intuitive expectation that larger systems would be more fragile. These quantum network topologies exploit the mathematical structure of quantum entanglement to create distributed error correction mechanisms that emerge naturally from the network architecture itself. But even these advances in quantum networking face fundamental limitations when we consider scaling teleportation to truly macroscopic objects. The distributed quantum computing approaches that might overcome computational complexity barriers don't address the physical challenges of maintaining quantum coherence across objects containing billions of atoms. The energy requirements alone present obstacles that seem insurmountable using any foreseeable technology. Maintaining quantum coherence in macroscopic systems requires energy input that scales exponentially with system size, potentially requiring power sources comparable to those used by entire cities just to preserve the quantum states of objects, measured in grams rather than atomic masses. The precision requirements compound these energy challenges in ways that push against fundamental physical limits. Quantum states are extraordinarily sensitive to tiny perturbations that would be completely negligible for classical systems. Temperature fluctuations measured in millionths of a degree, magnetic field variations smaller than Earth's magnetic field, and mechanical vibrations with amplitudes smaller than atomic diameters can all destroy quantum coherence irreversibly. Creating the controlled environments needed to maintain quantum coherence in macroscopic systems would require isolation techniques that exceed anything achieved in current physics laboratories. The most sophisticated quantum experiments currently operate in vacuum chambers, cooled to temperatures within thousandths of a degree of absolute zero, surrounded by multiple layers of magnetic and electromagnetic shielding. Scaling these environmental control requirements to accommodate macroscopic objects would require facilities of unprecedented size and complexity. The infrastructure needed to teleport something as simple as a grain of sand would likely be larger and more complex than the most advanced particle physics laboratories currently in operation. The measurement challenges present equally daunting obstacles that become increasingly severe as system complexity grows. Current quantum measurement techniques can handle individual qubits or small quantum systems with reasonable precision, but the measurement fidelity required for macroscopic teleportation approaches theoretical limits imposed by quantum mechanics itself. The uncertainty principle doesn't just limit our ability to measure individual particles precisely, it imposes fundamental constraints on how much information can be extracted from any quantum system without destroying the quantum states we're trying to preserve. These constraints become increasingly restrictive as we attempt to measure the complex quantum correlations that exist in large systems. Recent advances in quantum measurement theory have revealed techniques that can approach these fundamental limits for small systems under ideal conditions. Quantum-enhanced sensing protocols can achieve measurement precision that classical techniques cannot match, potentially providing the sensitivity needed for complex teleportation protocols. But even quantum-enhanced measurements face absolute barriers imposed by the mathematical structure of quantum mechanics. There are theoretical bounds on measurement precision that cannot be overcome regardless of technological advances. These bounds become increasingly restrictive as system complexity grows, suggesting that perfect measurement of macroscopic quantum states might be fundamentally impossible rather than merely technically challenging. The reconstruction challenges that follow successful measurement present their own set of seemingly insurmountable obstacles. After quantum information has been extracted from a complex system, it must be used to recreate the original quantum states with perfect fidelity at the destination location. Current quantum control techniques can manipulate individual qubits with reasonable accuracy, but the precision required for reconstructing macroscopic quantum states exceeds anything achievable with foreseeable technology. The control systems would need to position billions of atoms with precision measured in fractions of atomic diameters while maintaining quantum coherence throughout the entire reconstruction process. The timing synchronization required between measurement and reconstruction adds yet another layer of complexity that becomes increasingly difficult as system size grows. The classical information obtained from quantum measurements must be transmitted to the destination and used to guide reconstruction operations, while quantum states at both locations retain their coherence. For macroscopic systems, the amount of classical information required to specify complete reconstruction protocols could exceed the information content of the largest databases currently in existence. Transmitting this information quickly enough to complete reconstruction before quantum decoherence destroys the destination states creates communication bandwidth requirements that challenge physical limits on information transfer rates. Even using theoretical communication channels operating at the speed of light, the time required to transmit reconstruction information for complex objects might exceed the quantum coherence times of the systems waiting at the destination. This creates fundamental timing mismatches that could make faithful reconstruction impossible, regardless of advances in measurement and control technology. The philosophical implications of these technical barriers extend beyond engineering challenges into profound questions about the nature of identity and consciousness that have puzzled philosophers for millennia. Even if all technical obstacles could somehow be overcome, the fundamental requirement that teleportation destroys the original system raises troubling questions about personal continuity and identity. For conscious beings, the implications become particularly disturbing when we consider recent neuroscience research suggesting that consciousness might depend on quantum effects in neural microtubules and other brain structures. If quantum processes are essential for generating subjective experience, then teleporting a conscious being would require preserving not just the classical structure of their brain, but also the delicate quantum states that might constitute their inner awareness. The measurement process required for teleportation would necessarily destroy these quantum states at the source location, while creating identical states at the destination. From a physics perspective, the reconstructed person would be indistinguishable from the original in every measurable way. They would possess the same memories, personality traits, and behavioral patterns. But would they experience subjective continuity with their pre-teleportation existence? Or would they be a new consciousness that merely believes it has always existed? The question becomes even more complex when we consider that there might be no objective answer from the perspective of physics. If two quantum systems have identical states, they are equivalent in principle, with no physical test capable of distinguishing between original and copy. Recent research in consciousness studies has revealed that our intuitive understanding of personal identity might be fundamentally flawed even without considering teleportation. The neurons in your brain are constantly dying and being replaced. The molecules in your body are exchanged with the environment every few years, and even your memories are reconstructed rather than simply retrieved each time you recall past experiences. From this perspective, the discontinuity introduced by teleportation might not be qualitatively different from the natural processes that already maintain your identity across time. The person who wakes up tomorrow is already, in some sense, a reconstruction based on information patterns rather than material continuity. But the conscious experience of identity seems to involve more than just information patterns. There's something about subjective awareness that feels continuous and unified in ways that pure information processing cannot fully capture. Whether this continuity could survive the dissolution and reconstruction involved in teleportation remains one of the deepest mysteries in consciousness research. The ethical implications become even more complex when we consider that teleportation necessarily involves destroying the original system. This destruction isn't an unfortunate side effect that might be eliminated through technological improvements. It's a fundamental requirement imposed by the no-cloning theorem that prevents quantum information from being duplicated. The question becomes whether creating a perfect copy justifies destroying the original, even if the copy would be indistinguishable from the original in every measurable way. For inanimate objects, this trade-off might be acceptable if the practical benefits of teleportation outweigh the philosophical concerns about identity and continuity. But for conscious beings, the stakes become immeasurably higher because we're not just destroying and recreating matter, but potentially ending one stream of consciousness while creating another that believes it has always existed. The ethical weight of such decisions challenges our deepest assumptions about the value of individual consciousness and the nature of personal identity. These philosophical complexities might ultimately prove more challenging than the technical barriers that currently make macroscopic teleportation seem impossible. Even if we eventually develop the quantum technologies needed to teleport large objects, we would still need to grapple with profound questions about identity, consciousness, and the ethics of destroying and recreating sentient beings. The timeline for resolving these questions remains impossible to predict because they involve fundamental aspects of consciousness and personal identity that we don't yet understand well enough to analyze scientifically. The same quantum mechanics that enables teleportation might also be essential for consciousness itself. creating recursive puzzles where understanding consciousness requires quantum technologies that themselves raise questions about the nature of conscious experience. As research in quantum teleportation continues advancing toward larger and more complex systems, these philosophical questions will become increasingly urgent practical concerns. The scientific progress that brings us closer to macroscopic teleportation capabilities also forces us to confront fundamental mysteries about what it means to exist as conscious beings in a quantum universe. The journey toward human-scale teleportation represents far more than a technological quest. It's an exploration of the deepest questions about consciousness, identity, and the nature of existence itself. The answers we discover along the way will reshape not just our understanding of quantum physics, but our understanding of what it means to be human in a universe where the impossible becomes merely improbable, and the improbable becomes inevitable, given sufficient time and determination to push against the fundamental barriers that separate the quantum realm from our everyday experience of reality. The quantum universe continues revealing secrets that challenge everything we thought we knew about the relationship between information and matter, between consciousness and physics, between what we are and what we might become. As we stand at this extraordinary moment in scientific history, we find ourselves not just developing revolutionary technologies, but confronting the ultimate questions about the nature of existence itself in a cosmos governed by quantum mechanical principles that seem to offer pathways to achievements that previous generations could never have imagined. The story of quantum teleportation is still being written, and its final chapters might reveal possibilities that transcend our current understanding of what's achievable within the laws of physics. Whether those possibilities include the teleportation of conscious beings remains one of the greatest mysteries awaiting resolution as we continue pushing toward the seemingly impossible goal of making the quantum realm serve human ambitions that reach toward the stars themselves. The quantum teleportation protocols that seem to offer such revolutionary possibilities for information transfer might actually represent something far more profound than we initially understood. Recent theoretical breakthroughs suggest that the phenomenon we call quantum teleportation could be revealing fundamental aspects of how reality itself operates at the deepest levels. Consider what happens when we examine the mathematical structure underlying quantum teleportation more carefully. The equations that govern this process don't just describe how information moves from one location to another, they reveal deep connections between quantum mechanics and the geometry of space-time itself that challenge our most basic assumptions about the nature of physical reality. The holographic principle that emerges from these mathematical relationships suggests that all the information contained within any volume of space might actually be encoded on its boundary. This radical idea transforms our understanding of how quantum teleportation works, by revealing that information transfer might not involve movement through space in any conventional sense, but rather changes in how information is distributed across the fundamental structure of reality. These insights are forcing physicists to reconsider whether quantum teleportation represents a technology we might eventually master, or whether it's revealing something much more fundamental about the nature of existence itself. The same mathematical formalism that describes teleportation also appears in theories of black hole physics, cosmology, and the deepest levels of quantum field theory. The implications extend far beyond the practical challenges of scaling teleportation to larger systems. If the holographic principle is correct, then the distinction between information and physical matter might be far more fluid than we previously imagined. The boundaries between what exists here and what exists there, between what is real and what is information, begin to dissolve when examined through the lens of quantum teleportation theory. Recent experiments using quantum computers to simulate holographic systems have provided tantalizing hints that these theoretical connections might reflect genuine features of physical reality. Researchers have successfully created quantum systems that exhibit the mathematical signatures predicted by holographic theories, suggesting that the deep connections between information and space-time geometry are more than mere mathematical curiosities. These quantum simulations don't create actual wormholes or manipulate space-time directly, but they demonstrate that information can behave in ways that seem to transcend conventional notions of locality and causality. The quantum states involved in these experiments exhibit correlations that persist across separations where no classical signal could maintain such connections. The experimental techniques required for these demonstrations push quantum control systems to their absolute limits. Creating quantum states that exhibit holographic properties requires maintaining precise correlations between hundreds of individual qubits simultaneously, with timing precision measured in nanoseconds and control accuracy approaching the theoretical limits imposed by quantum uncertainty. Yet the results consistently confirm theoretical predictions that seemed impossibly abstract when first proposed decades ago. The quantum mechanics that enables teleportation appears to be revealing aspects of reality that transcend our everyday experience of space, time, and causality in ways that challenge the foundations of classical physics. The energy scales involved in these quantum simulations remain modest compared to what would be required for macroscopic teleportation, but they're providing crucial insights into how quantum information behaves under conditions that approach the theoretical limits of what's physically possible. Each experiment reveals new aspects of quantum behavior that weren't predicted by existing theories, suggesting that our understanding of quantum mechanics itself remains incomplete. The measurement techniques required to probe these exotic quantum states have driven the development of sensing technologies that achieve precision levels previously thought impossible. Quantum sensors capable of detecting individual photons, measuring magnetic fields with atomic scale resolution, and monitoring quantum states without destroying them are becoming essential tools for exploring the frontiers of quantum physics. These quantum sensing advances are finding applications far beyond fundamental physics research. Medical imaging systems based on quantum sensing techniques can detect biological processes at the molecular level with unprecedented sensitivity. Navigation systems using quantum sensors can operate independently of satellite signals while achieving positional accuracy measured in centimeters across continental distances. The industrial applications of these quantum sensing technologies are creating economic incentives for continued investment in quantum research that extends well beyond the academic pursuit of fundamental knowledge. Companies developing quantum sensors for oil exploration, mineral detection, and infrastructure monitoring are generating revenues that support continued advances in quantum technology development. As we reach the end of this extraordinary journey through the quantum realm, we find ourselves standing at the threshold of possibilities that would have seemed like pure fantasy just decades ago. We've witnessed how scientists have achieved genuine teleportation through the mysterious dance of quantum entanglement, transferring information across vast distances without any physical particles making the journey. We've explored the elegant mathematics of the no-cloning theorem that makes this impossible technology not just possible, but inevitable in a universe governed by quantum mechanical principles. Yet the path toward human-scale teleportation remains fraught with barriers that challenge the very limits of what physics might allow. The exponential scaling of quantum complexity, the fragility of quantum states in macroscopic systems, and the staggering energy requirements all conspire to keep true teleportation confined to the microscopic realm, at least for now. But perhaps the most profound realization is that quantum teleportation has already transformed our understanding of reality itself. It reveals a universe where information and matter, space and time exist in relationships far more intimate and mysterious than our everyday experience suggests. Whether we'll ever step into teleportation chambers or simply continue marveling At this quantum impossibility made real, one thing remains certain. The universe continues revealing secrets that challenge everything we thought we knew about the nature of existence itself. The quantum realm beckons with possibilities we're only beginning to imagine, and the story of teleportation is far from over.